Hello everybody and welcome back to our regular languages and finite automata class. This is unit 9 and in this unit, as I have promised, we are going to wrap up the regular languages section of our class and effectively the finite automaton part of it. And what we are going to do actually in this class is we're going to take a look at the limitations of regular languages. You've seen so far models for regular languages in the form of deterministic finite automaton, non-deterministic finite automata, as well as the regular expressions way of expressing regular languages. And now we are at the point that we know really all the powers of the regular languages, and we need to take a look and see, are there other things than regular languages? And the answer is yes. And to see how we can look at a language and show whether this language is indeed regular or not. So to understand what the power of finite automata is, we also must understand their limitations. The way that we can look at finite automata and look and decide about their limitations is looking and trying to prove that there are certain languages that are beyond the reach of finite automaton, any finite automaton, and that there is no such finite automaton that can recognize these languages, and therefore these languages will be non-regular. So how can we do this, and what are the examples of such languages? So for this, let's take a look at this very simple language here. We call language B to be the set of all the strings that are in the form of 0 to the n, 1 to the n, such that n is greater than or equal to 0. What does this mean? It means that language B is made of all strings that start with a number of zeros and end with a number of ones. So the first portion of the string has zeros in it, and the second portion of the string has ones in it, and then the number of zeros and the number of ones are equal. And this could take any repetitions of zeros. Now, is this a regular language? If I ask you to look at this language and show whether this is a regular language or not. First of all, by the end of this unit, we will actually come up with a formal proof about how we can actually do this and show that this language is not regular. Indeed, this language is not regular, and then we'll have to basically look at what it means for a language to be non-regular. So, at the first look at this language, you might say, well, fine, isn't this language made of two strings of all zeros and strings of all ones? So that's a concatenation of two strings. And then what I'm going to do is I'm going to break this language into two parts. Language A that recognizes all zeros, and language B, or for this matter, let's call it language Q, that recognizes all ones, and then I concatenate these two together. Well, that is actually true. However, there's one restriction on this concatenation. That means that the second part of your machine, the part that recognizes ones, must remember how many zeros the first part of your language or machine accepted, and then match that up. So if you don't really look at n very critically, and that n could be any number greater than or equal to 0, you would say, well, fine, I'm going to make a machine that has n states to recognize zeros, and then I match that with another n states to recognize ones, and then I'll be good. However, the problem is that, remember, a finite automaton is a finite automaton, meaning that the number of states in this machine must be finite. The problem is that any kind of automaton that you want to create to recognize this language and the strings of this language seems to need to remember how many zeros it has seen and then match them up with how many ones it will see. The problem is that n could be an infinite number, n could be any number, and we cannot really design our finite machine to recognize any number. because our memory is limited in that in order to keep track of how many zeros you have seen, you seem to need to have an infinite number of states, and since we can't have an infinite number of states, therefore we don't seem to be able to build a machine with finite number of states to recognize the language B. So what we're going to do is we're going to present a method for proving that languages such as B that we saw in the previous slides are not regular. There's one question that you might ask, is that doesn't the argument that we already gave that in order to recognize a language like B, we need to have an infinite number of states, isn't that enough to prove that this language is non-regular, because there is no limit on the number of zeros that your machine can see, so that it would be able to match it up? The problem is that that although it does appear at the first look in our previous language that there may be a need for infinite number of zeros and ones, or infinite number of states to recognize, this seemingly inability on our part to build a machine, a DFA, to recognize the language, it may be a good idea to show you that the language is not regular, but it's not a formal proof. We must formally prove that the language is not regular. So just the argument that, oh, I just seem to need an infinite number of states, does not really fly mathematically as proof. For example, let's take a look at these two languages, C and D. Let's say we have a language C such that it's composed of all strings with an equal number of zeros and ones in them. Is this a regular language? Or we're just going to just slightly change the formulation of language C and come up with language D. Now, in language D, we want to create it's made of strings that have equal appearances of 0, 1, and 1 zeros as substrings. Is this a regular language? So at first sight, you look at the two languages, C and D, and you basically could say, well, I can kind of substitute this 0, 1 as a symbol 0, and then this 1, 0 as a symbol 1, and then as such, then these two languages seem to be the same, and we kind of sort of could have a very solid guess that the language C is not regular. In fact, we are going to prove that languages such as language C are not regular. But it's very interesting to know that actually language D is a regular language. You can make a finite automaton, a DFA, that recognizes language D. But there's no finite automaton that recognizes language C. So our seeming inability of not being able to come up with a machine just right off the bat doesn't really prove the language is not regular. So for this matter, we would actually have to have a solid argument, a solid mechanism of looking at a language and proving its irregularity, than just stating that we just couldn't find a DFA to recognize it. So just keep in mind that sometimes your intuition may actually kind of mislead you, and just to avoid this kind of misleading situations, we are going to formulate a proof of non-regularity that would be beyond any uncertainty or any doubt. As we have discussed earlier in the class, that mathematical proofs should be precise and completely beyond any doubt. So our technique for proving non-regularity is effectively from a very important property of regular languages, and it's about an important theorem about regular languages. And this theorem traditionally is called the pumping lemma. This theorem states that all of your regular languages have a very special property, and if we can find a language that does not follow this special property, effectively we proved is a non-regularity. And if we want to show a language is regular, we can actually try to prove that that language actually satisfies this property. The property that we have here about regular languages is effectively fairly simple. It states that if you have a regular language then all of its strings can be pumped, and therefore it's called the pumping lemma, interestingly enough. Um, and let's see what this means. What this means that that strings in a language can be pumped. So effectively, the pumping lemma unofficially states something like this: that if you have a regular language, then if you take all of its strings in the regular language, and if the strings are at least of a certain length, then you can actually pump this string, and for this string still to be in the same language. So let's just visualize it. Let's say that you have a language that recognizes, or rather a finite automaton that recognizes some language, like a language that ends with a 1, right? So if you look at this machine and look at how many states there are in it, then you could come up with a number called the pumping length, that if you have any string in your original language that has at least the length pumping length, then you can break it into a number of substrings, actually 3 sections, and then you can take the middle section and then repeat it as many times as you need or as you want, and the resulting string will still be in your language. And so the language being pumped effectively means this: if you can split into 3 substrings, take the middle section and repeat it any number of times, that is basically pumping your string, and you come up with a longer string, but that longer string is still going to be in your language. In fact, it could be a shorter string, so if you pump it 0, basically take the middle section out, your language, your string will still remain in the language. So this is effectively what it means, the pumping lemma and pumping a language. So that's an informal way of stating the pumping lemma. Let's actually take a look at a formal formalization rather of the pumping lemma. So the pumping lemma, according to the Substairs books, is a theorem 1.70, and it states that if A is a regular language, then there is a number P, or we call this the pumping length, where if you find a string S, effectively any string in language A of at least length P, then the string S may be divided into 3 pieces, X, Y, and Z, that satisfies these 3 conditions. Condition number 1, if you pump, or rather repeat the middle section Y any number of times, so you see X, Y to the I, Z, for any number of repetitions of Y. So I could be 0, 1, 2, 3, or an infinite number. So if you repeat this middle section Y any number of times, then the X, Y, I, Z, the resulting string, will be still in language A. The length of the middle section must be greater than 0. In fact, this is a small typo here. So the length P must be strictly greater than 0. I mean, length of Y. So Y cannot be empty. And then the length of the first section, including Y, so the first 2 sections, if you put the 2 together, its length must be less than or equal to P. If these 3 conditions are met, then we say that the string is pumped, the string S is pumped, and it belongs to the language, and that if you have a language that satisfies these properties, that for all of its strings greater than the pumping length, these 3 conditions are satisfied, then you effectively have a regular language. A couple of things, the notation wise, the notation of length is effectively these 2 vertical lines. So the length of a string is, when we put the length, is in the absolute value, and I is and then Y to the I, or a string raised to the power, means that we take that string and repeat it that many times. So what this string means, what this lemma means, is that when S is divided into X, Y, Z, you can have either X or Y be empty strings, but you cannot have sorry, you can have either X or Z to be an empty string, but the middle section must be non-empty. And also the length of the combined first two sections must be less than or at most P, equal to the pumping length, and that the pumped string will effectively remain in your language. So one of the things that we will actually utilize is we actually utilize all these three sections for the pumping lemma for our formal proofs. Basically, we look at a language that's in the look at a string that's in the language. We break it down into X, Y, and Z for the middle section not to be empty. We most of the times when we need to simplify our process, we invoke the property number 3 here, effectively the length of your first section of the string to be at most P, and that most of the time simplifies the proof of non-regularity of some languages much more straightforward. And then from that point on, we'll effectively start going and looking further down into finding an example of a string that cannot be pumped and therefore the language not to be regular. So let's take a look at the idea here for a formal proof of the pumping lemma. Okay, the idea here is that if M is a deterministic finite automaton, effectively the 5-tuple Q sigma delta Q sub 1 and F, that recognizes A, because we suppose that A is a regular language, right? So the idea is that if A is regular, then some DFA M will recognize it. Let's suppose that Q sub 1 is the start state. And what we are going to do is that we're going to assign the pumping length of this DFA, or the pumping length of this language to be equal to the number of states in M. So we say that if M has a set Q states, then if the length of Q is some number, we choose that number to be the pumping length. Now from this point we show that any string in S, any string S in A that has a length of at least P can be broken into the three pieces X, Y, and Z that satisfies our three conditions, namely that Y, the middle section, is non-zero, the combined length of X and Y is at most P, and that if we take the middle section and pump it up or down any number of times, then that language will be or that string will be in the language. There's one thing here that we also can kind of remember, is that if A is a language that has a bunch of strings and none of its strings has is greater than length P, what about that? Is that still valid? If you have no strings with lengths greater than P, then your statement is still true. Effectively, it's vacuously true, in that if there are no strings in A that have at least length P, then you have an empty set of strings with length at least P, and therefore all of them, namely none, because there are no such strings, can be pumped. So your statement would be still true. Obviously, if your language has a finite number of strings in it, it is regular, right? Because you can create a machine with a finite number of states to recognize all of its strings. So for this matter, from this point on, we assume that there are strings in our language that have at least length P, and that they can be pumped. So the idea that we're going to use is going to be based on a very simple principle. It's called the pigeonhole principle. It's a fancy name for stating a very obvious fact that if you have P items, or rather P pigeons, and you want to place them into fewer than p holes, then at least one of the holes will have more pigeons in it. So the proof idea here is based on the pigeonhole principle. So let me actually draw this down to show that this is quite obvious. So if you have effectively some holes, and then you have some pigeons, and my drawing is pretty awful, so I'm not just going to draw pigeons. So let's suppose that you have p pigeons, and then you have n holes, and that n is less than p, right? So the pigeonhole principle states that at least one of these holes will have more than one pigeon in it. How do you look and see that? It's obvious. So you start with first hole and put the first pigeon in, the second hole, the second pigeon, the third hole, the third pigeon, and then you keep going on, and then the nth hole which will contain the nth pigeon. So this is the first n pigeons that went into the p holes, and then you end up with some unassigned pigeons, and so which means that you can put all of these unassigned pigeons at least in one of these holes, which means that at least one of these holes would have more than one pigeon in it. So we use this idea to perform our formal proof of the pumping lemma. So again, back to the proof idea. Let's say that we had a finite automaton, and this finite automaton we wrote it formally as m equal q sigma delta q sub 1 and f. So let's say that the length of q is equal to p. So we have a machine with at least p states in it. So all these guys will be my machine and the accept states. So this is going to be my machine M. Okay, so I also know that the first state is called q sub 1, which is this guy. And then I have a bunch of accept states, so this is going to be f. Then the idea says that if I have a string, and let's say that s belongs to a, okay, so I have a string, and I break this string into a bunch of symbols, w1, w2, 2wk. Actually, let's call it wn. And so n is greater than p. So I have a, or rather greater than or equal to p. So I have a string that is made up of a bunch of symbols. So since the s of n, the length of s is greater than or equal to p, right? It means that if I start with w sub 1, I end up with some w sub n, and this n is going to be greater than or equal to p. So I know from my formal computation, my machine starts from q sub 1, and then reads w sub 1, goes to q sub 2, reads w sub 2, goes to q sub 3, and so this keeps going until it reads w sub n and goes to q sub n plus 1. See, when you start in q sub 1 with some w sub 1, you go and you keep going on and on and on in some state. Okay, so effectively the number of states that I have is going to be n plus 1 sequence of states. Okay, so if I feed a string with n symbols in it, it would have to have n plus 1 states to process. Starts from q sub 1, then keep going on and on and on. So since n is greater than or equal to p, then n plus 1 is going to be strictly greater than p. Okay, so this is the fact here. Since we have n length of the string, and n is at least p, it could be equal to p. So if I add 1 to it, then it could be p plus 1 or more. And therefore, I have a sequence of states whose number is greater than the number of states in my machine. So what I have here is that my machine M has p states. So equal to holes, and my sequence to accept S has greater than p states. Call these pigeons, right? So I have p states, I have p holes, and more than p pigeons, and therefore at least one of these states must be a repeat state. Okay, so then according to the pigeonhole principle, so what I ended up here is that S, the length of S is greater than or equal to p, then the length of sequence to accept S is greater than p, but the length of Q is equal to p. So I have more states in the sequence than states in M. Therefore, at least one must repeat. Okay, so how does this look like? Let's say that I start from Q sub 1, and then I read W sub 1, and then I go to Q sub 2, and then I read W sub 3, the W sub 2, and then I go to some state, and then I keep going from state to state, and finally I go to Q accept. I know that these are more than 1, more than p, and I know that at least one of them is going to be a repeat state, which means that some Q sub I here is going to be repeated, right? So what does this mean? So let me just write it just with numbers. So let's say that you start from Q sub 1, you read a symbol, you go to Q sub 3, for example, you read another symbol, you go to Q sub 10, for example, you read another symbol, you go to Q sub 8, and so on and so forth. And then at some point, you revisit one of these states. Let's say Q sub 10, you revisit it. And then you keep going until you go to Q accept. Okay, so this is the sequence of your states to accept. And since we have more states in this sequence than we have states in the machine, at least one of these guys must be repeated as we keep processing, right? So if you draw this, we start from some state, Q sub 1, and then we keep processing until we go into, let's say, Q sub 10 here, right? And then from this point on, it keeps going into some states and then comes back to Q sub 10. So this is the first appearance of Q sub 10. So Q sub 10, first appearance. And then this is the second appearance. And then you keep processing the rest of this string if you have no other repeated states until you reach some Q accept. Okay, so effectively we visited at least one state twice. So this is awesome. Then we can actually do something like this. We can go in here and call this piece X and call this last piece Z, and this piece that starts with the first appearance of the repeated state until the last appearance of the repeated states, and then we call this Q, this state Y. I mean, this piece of my string, I call it Y. So let's suppose that I start from Q sub 1, and then I go to Q sub K, go to Q sub M, and then go to some Q sub F, and then from here I keep going to some Q sub 9 and stuff until I revisit this Q sub F, because remember I said at least must have at least 2 of these states, and until I go to Q accept. So that's going to be the sequence of my strings. So what I'm going to do is that I'm going to assign this portion of my string as Y. I'm going to assign this portion of my string and I call it X, and I'm going to assign this portion of my string and call it Z. So let's call this Q sub U and Q sub T. Okay, so basically pick the first appearance of the repeated state and the second appearance of the repeated state and call that portion of your string Y, and then the first portion will be X and the second portion will be Z. Now if you do this, then all of the conditions of your pumping lemma are going to be met. Why? Let's take a look at the first condition. If you take this repeat state and then repeat it I times, it means that you start from some state and then you go and then you go and then you go and then you go a number of times. Okay, and this does not change the rest of this sequence, which means that even if you repeat this portion any number of times, you start from start state and you end in accept state. So this pumped string will be still in A. So that's condition number 1. Condition number 2 is also met. Condition number 2 means the length of Y is greater than 0. And it is true because it at least have the first appearance of the state and the second appearance of the state, which means that there's at least one symbol here. So the length of Y will be greater than 0. Secondly, this third portion of your pumping lemma condition is also met. The length of X and Y is less than or equal to P. And the reason that is so is because you see we had P states in our machine, and since we already have a start state Q sub 1 and we go through the sequence of our states to get to the second repetition of my pigeonhole principle, this means that all of these guys put together, including the first and the second appearance of my repeat state, must be in the first P states for the pigeonhole principle to satisfy. So the sequence that contains the repetition will have to occur in the first P sequence of states, and therefore the length of X and Y together is going to be less than 3. So the 3 conditions are met. Condition number 1 that says that pumping the middle section will not change the acceptance of our string. Condition number 2, which means that the middle section will have at least one element in it. And condition number 3, which means that the first 2 portions of my string, or the portions that contain the repeat states, must have the length at least P. So this is the proof idea of my pumping lemma. And next I'm going to go in the next video and make that into the formal proof, and we'll see a bunch of examples to show the non-regularity of some languages.